Diving deep into perhaps the biggest puzzle in modern physics. It feels like we've built this incredible detailed map of the universe, but there's this fundamental contradiction right at the heart of it.
That contradiction is absolutely central. It's the clash between our two greatest theories of reality, general relativity and quantum mechanics.
Right, Einstein's general relativity, gravity, space-time, the big stuff. Works perfectly.
For the very large, yes. Planets, stars, galaxies, it's all smooth, continuous, deterministic,
And then you've got quantum mechanics, the rule book for the incredibly tiny. Particles, forces, probabilities, fuzziness.
Also astonishingly precise in its own world, the subatomic realm.
So both work fantastically well on their own turf.
Exactly, spectacularly well. But the moment you try to bring them together, say in a black hole singularity or right at the Big Bang,
The math just falls apart.
completely. You slam into these uncontrollable mathematical infinities, predictions that are just, meaningless.
Your sources call it the single greatest unsolved problem in physics. We just don't have a quantum theory of gravity.
We don't. And that means our understanding is fundamentally incomplete at the extremes.
Which leads us to needing something.
Yeah.
Pretty radical. Something to bridge that gap. And that's where string theory enters the picture, right? With this wild idea that the basics aren't points.
It is a radical departure, absolutely.
Oh.
The premise laid out right there in the sources is that if you could zoom in way, way further than we ever could, down to the Planck scale.
Which is mind-bogglingly tiny, 10 to the minus 35 meters.
Unimaginably small, yes. You wouldn't see point-like particles. You'd see tiny one-dimensional filaments, loops or strands of pure energy.
Strings.
Strings.
Like actual tiny strings, cosmic rubber bands.
It's a decent analogy, yeah. Vibrating at incredible frequencies. And the core idea, the central thesis in all this material, is that all the different particles we see, electrons, quarks, photons, everything, and all the forces, including gravity, they're just different ways these fundamental strings vibrate, different emergent harmonies.
The cosmic symphony idea. I like that. It's like a violin string playing different notes.
Exactly. A C note, a G note.
A fundamental string vibrating one way is an electron. Vibrated differently, it is a photon. And maybe another vibration. It's the graviton, the gravity particle.
That is precisely the picture. It suggests this incredible underlying unity, all that diversity we see, the whole particle zoo. It's not different ingredients, it's just different vibrational modes of one single type of thing.
Okay, that's a powerful concept. So our mission for this deep dive, based on these sources, is to really unpack how this whole vibration idea attempts to unify everything. And, what the implications are, and the problems, too. Let's start right at the source of the trouble, then. Why do point particles lead to those infinities when you mix quantum mechanics and gravity? What's fundamentally wrong with points?
Well, the standard model of particle physics, which does treat particles as points, has been incredibly successful. Let's be clear on that.
Oh, absolutely. It describes three forces: strong, weak, electromagnetic, all the known matter particles, quarks, leptons.
And its predictions, verified to amazing precision. Think about the Higgs boson discovery. That was a huge confirmation.
One of the greatest scientific achievements, full stop.
No question. But, and this is the crucial but highlighted in your sources, it has these acknowledged deficiencies. It's clearly not the final story.
Like the fact that it just leaves gravity out entirely?
That's the elephant in the room, yes. Doesn't include gravity, incompatible with general relativity. But it's more than that. It doesn't predict fundamental values, like particle masses or how strong the forces are. These numbers, they're just measured experimentally and inserted by hand.
So you have to plug them in. The theory doesn't tell you why an electron has the mass it does.
Nope. There are over 24 of these free parameters, these knobs you have to set based on experiments. The theory works once you set them, but it doesn't explain why they have those values.
So it calculates interactions beautifully, but doesn't derive the fundamental properties from the theory itself.
Precisely. And it also has nothing to say about dark matter or dark energy.
Which is, 95% of the universe?
Around that, yeah.
Yeah.
Huge gap. And other puzzles, too, like neutrino oscillations or why there's more matter than antimatter.
Okay. So the standard model is brilliant but incomplete. It describes the what incredibly well for three forces, but not the why, and it misses gravity entirely.
Right. Now, the switch from 0D points to 1D strings, that directly tackles the quantum gravity problem. Think about how point particles interact in quantum field theory. Their path is a 1D line in spacetime, a world line.
Okay.
When two points interact, like say an electron emitting a photon, their world lines meet at a single zero-dimensional point, a sharp corner.
And that's the problem point, literally.
Especially for gravity, yes. That zero-size interaction point is where the calculations blow up. You get infinities, division by zero, essentially, in the math.
A string isn't a point. It moves through time tracing out.
Huh?
Not a line, but a surface, a world sheet.
Exactly, like a tube or a ribbon moving through space-time, a 2D surface.
And that makes all the difference.
It's the crucial difference. When strings interact, say, two strings merge into one or one splits into two, their world sheets join up smoothly. There's no single sharp point of interaction.
It's smeared out.
The interaction is smeared out over a tiny region. And this smoothing, this lack of a zero-size point, is the essential mechanism your sources talk about. It tames those infinities, those ultraviolet divergences.
So the very fact that a string is extended, not point-like, is what fixes the math for quantum gravity.
That's the core insight. The extended nature allows it to vibrate, giving rise to particles, and it smooths out interactions, allowing for a sensible theory of quantum gravity. The two aspects are linked.
That's really elegant. The solution comes packed inside the new idea itself.
Okay, so they vibrate. Let's really get into this universe as music thing. How does vibration make everything?
Okay, so imagine these strings are the only fundamental ingredient, the only type of instrument in the whole cosmic orchestra.
Just strings. Then every particle we know is just a different note played by these strings. An electron, that's one pattern of vibration. A photon, a different pattern. A quark, yet another.
And like notes on a guitar string are quantized. You get specific frequencies, right? Harmonics.
Exactly. You can't just have any vibration. Only certain discrete modes, specific energy levels, are allowed by the quantum rules.
And energy equals mass, EMC squared.
Precisely. So these quantized vibrations directly lead to a discrete spectrum of particles, each with a very specific mass, determined by its vibrational energy.
Which is a totally different picture from the standard model. That felt more like finding a bunch of different instruments, electrons, quarks, photons, and just writing down their properties.
Yeah, the standard model, as we said, needs those 24 parameters specified by hand. Like you have to tune each instrument manually without knowing why it has that pitch.
But string theory wants to be.
A symphony played on a single type of instrument. The incredible variety of particles and forces we see isn't fundamental, it's an emergent property. It arises from the rich harmonic possibilities of this single underlying string. It promises a much deeper unity and mathematical elegance.
And the sources mention two basic kinds of strings, open and closed.
That's right. You have open strings, which are like little segments with two distinct endpoints. Think of a piece of thread.
Okay. And what are they associated with?
Primarily with the particles that carry the standard model forces. The photon for electromagnetism, the W and Z bosons for the weak force, the gluons for the strong force. Those tend to come from open string vibrations.
And then the closed strings, they're loops.
Yes, continuous loops like tiny rubber bands.
Oh.
And this is where gravity makes its appearance.
Ah, so gravity comes from the closed loops.
The vibrations of closed strings naturally give rise to the graviton, the particle of gravity. So the theory has this sort of natural architectural separation built in. Open strings for gauge forces, closed strings for gravity.
Okay, so one string type, open or closed, vibrating in different ways, makes all the particles and forces. Let's drill down. How exactly does vibration give us numbers? Like mass, spin, charge.
Right. How does the music define the players? The most direct connection is mass. It's simply the energy tied up in the string's vibration.
More vibration, more energy.
More energy, more mass via EMC day. Higher frequency, higher amplitude vibration means a heavier particle. Less energy in the vibration means a lighter particle.
So the very lightest particles, like the photon or this graviton, they'd be strings barely vibrating at all, the lowest possible energy state.
That's exactly right. In consistent string theories, the lowest possible energy modes can be, and often are, perfectly massless. This gives a natural origin for particles like the photon and graviton, which we know are massless.
And heavier particles are just the same strings, but buzzing more energetically.
Precisely. They're the progressively higher and more energetic vibrational states of the very same fundamental entity.
The sources mention a formula, like m squared is related to n. What's n?
Yes, M-N-A from early bosonic theory. N is basically the number operator. It counts the total excitation level, the number of units of vibration or harmonics the string has. Higher N means more vibrational energy, hence more mass.
The key thing being, Mass isn't arbitrary anymore.
That's the huge potential payoff. Mass becomes a prediction derived from inter-excitation level n. It's not a free parameter you measure and plug in like in the standard model. It's, in principle, calculable.
That's a massive shift, transforming mass from input to output. And you said it predicts the graviton without being asked.
Yes, that was a critical discovery. The theory just naturally contained a vibrational mode with the exact properties massless spin 2 needed for the graviton. That really made people sit up and take notice.
Okay, mass from vibrational energy. What about other quantum properties? Spin, charge.
They're also encoded in the intricate dance of the string's vibration. Spin, for instance, relates to the sort of rotational properties of the vibrational pattern.
So simple vibrations might be spin 0.
Right, scalar particles. Then you can have modes with 1 unit of angular momentum. Effectively, those are spin 1, like at the photon. 2 units give spin 2, the graviton.
But what about matter? Electrons, quarks, they have spin 12. Half-integer spin. How does that work?
Ah, that's where a crucial addition comes in, something called supersymmetry, or SES-USY.
Okay, hold that thought. Because before SES-USY, the sources mention a big problem with the first version, bosonic string theory. Something about a tachyon.
Yes, the tachyon problem. The original bosonic string theory only described bosons' force carriers, and its simplest vibrational state, the ground state where Na0, essentially, turned out to have a negative mass squared.
Negative mass squared. What does that even mean?
It implies imaginary mass. That particle was called a tachyon. Tachyons are bad news.
No.
Physically, they suggest the vacuum itself is unstable. They can travel faster than light in the math. It's physically unrealistic. It looked like a deal breaker.
So how did they fix it? You mentioned supersymmetry.
Exactly. Supersymmetry is this hypothesized symmetry that connects bosons, integer spin, and fermions, half interspin, like matter particles. It predicts every known particle has a superpartner with spin differing by 12.
So the electron would have a selectron, the photon a photino.
Those are the names, yes. When you build a string theory that includes supersymmetry, a superstring theory, you introduce new vibrational modes corresponding to these fermions.
And these new modes fix the tachyon.
Miraculously, yes. The mathematical contributions from these new fermionic modes precisely cancel out the negative mass squared of the bosonic tachyon. The tachyon disappears from the spectrum in superstring theory.
Wow, okay, so SUSY solves that instability, but it does more, right? The original theory couldn't even describe matter.
Correct. Bosonic string theory had no place for fermions like electrons or quarks. Superstring theory, by incorporating SUSY, naturally includes both bosons and fermions. It can, in principle, describe both forces and matter, making it a much more plausible candidate for a theory of everything.
So SUSY wasn't just patching a hole. It was essential for making the theory capable of describing the universe we actually see, with matter in it. Okay, so we have vibrating strings open and closed. SUSY helps include matter and fixes the tachyon. But where's all this vibrating happening? The sources say string theory makes this startling and non-negotiable prediction about space-time itself.
It really does. It's one of the most counterintuitive but mathematically required aspects. For the theory to be consistent, to avoid mathematical anomalies that break fundamental principles like Lorentz invariance or quantum unitarity.
Basic requirements for any physical theory.
Right. For those things to hold, the universe cannot just have the 4 dimensions we know, 3 space, 1 time. It must have more spatial dimensions.
More dimensions. How many?
Well, the early bosonic theory needed 26 dimensions in total. But the superstring theories, the ones with SUSY that seem more realistic, require 10 space-time dimensions, 9 space, 1 time.
And then there's M theory.
M theory, which seems to unify the different superstring theories, lives in 11 space-time dimensions.
Okay, wait. 10 or 11 dimensions. We really don't see those. I see length, width, height, and time unfolding. Where are the other 6 or 7?
That's the immediate, perfectly valid question. The idea is compactification.
Compactification, meaning?
Meaning the extra dimensions are curled up or compactified into an incredibly tiny space. So small, likely around the Planck length again, that we just don't perceive them in our everyday lives or even in our most powerful experiments.
Can you give me an analogy?
The classic one is the garden hose. From far away, it looks like a one-dimensional line.
Right.
But if you were an ant walking on it, you'd see it has a surface. You can walk along the length, the big dimension we see, but you can also walk around its circumference, a second, small, curled up dimension.
Ah, okay. So we're like the person viewing the hose from afar, only aware of the large dimensions. These extra 6 or 7 dimensions are curled up like the hose's circumference, but just unimaginably smaller.
That's the picture. But here's the absolutely critical part. The shape of that tiny curled up space is not just some detail. It fundamentally determines the physics we see.
The geometry of the hidden dimensions dictates the laws in our dimensions. The source called it a resonating chamber.
It's a perfect analogy. The strings vibrate within this compactified space, and just like the shape of a violin or a French horn determines which sound frequencies resonate and which don't, the geometry of these extra dimensions constrains the possible string vibrations.
So the shape selects which notes, which particles and forces are allowed in our universe.
Exactly. The geometry directly determines the laws of physics we observe.
And for superstring theory, these shapes have to be very specific things called Calabi-Yau manifolds.
Yes, these are complex, six-dimensional mathematical shapes that have the right properties to allow some of the supersymmetry from the 10D theory to survive down into our 4D world, which seems necessary to match observations.
And the source gave an example, like the 3 generations of matter particles, electron, muon, tau. They're like copies of each other. Could that come from the shape?
That's one of the most exciting possibilities. The existence of exactly 3 generations might be tied to a topological feature of the Calabi-Yau manifold, like, say, the number of holes or handles it has.
So a string vibrating in a certain way but interacting differently with 3 distinct holes in the hidden dimensions might appear to us as 3 different particles.
It could. That's the kind of deep connection the theory suggests. The geometry isn't just a passive background. It's an active author of its laws.
Wild. And this understanding led to M theory, the second superstring revolution.
Yes, around 1995, physicists realized, partly through studying these geometries and dualities, that the 5 different superstring theories known at the time weren't actually separate. They were just different facets or limiting cases of a single underlying theory in 11 dimensions.
M theory.
Mystery, mother, membrane. Nobody definitively knows, partly because the theory itself isn't fully understood. But discovering these dualities, these hidden connections, showed this stunning hidden unity. It suggested all consistent quantum gravity theories involving strings might be part of one single structure.
Okay, so the stage is set. Higher dimensions, curled up into complex shapes that dictate the possible string vibrations, the particles and forces we see. Now let's talk about those forces emerging. The sources say this unification is the most compelling aspect.
It really is. This is where string theory potentially delivers on the theory of everything promise. The forces aren't bolted on. They emerge as naturally and inevitably as the matter particles.
And gravity is the star player here, the greatest triumph.
Without a doubt. Remember, the standard model has no place for gravity. You'd have to manually add a graviton. In string theory, gravity is required.
How so?
That lowest energy vibration of a closed string loop. It automatically, unavoidably, has exactly the properties needed for the graviton. 0 mass, spin 2, and universal interaction with energy. The theory predicts gravity whether you asked it to or not.
So it's not just a possible node, it's baked in. An automatic and unavoidably one of the notes from closed strings.
Yes. Discovering the spin 2 mode was the pivotal moment. And linking back, remember the smeared out interaction from the world sheet.
Right, that fixed the infinities.
Well, that mechanism allows string theory to give finite, well-defined, and sensible answers for quantum gravitational interactions. It's still arguably the first and only known theoretical framework that seems capable of doing this consistently.
That's a huge statement.
Okay.
Gravity from closed strings, the other forces, electromagnetism, strong, weak, come from the open strings.
Correct. The lowest energy vibration of an open string is a massless spin 1 particle. That's the photon, the carrier of electromagnetism.
And the heavier force particles, WZ, gluons.
Those correspond to more massive spin 1 vibrations of open strings.
But you mentioned open strings have endpoints.
Yeah.
And they have to be attached to something, D-branes.
Yes, D-branes. Think of them as multidimensional membrane-like surfaces embedded within the full higher dimensional space. And there's a crucial rule. The endpoints of open strings must lie on these D-branes. They're stuck to them.
Okay. So why are that important for the forces?
Because the configuration of these D-branes is what determines the specific gauge symmetries, the mathematical structures underlying the forces.
How does that work?
If you just have open strings whose endpoints can move around on a single D-brane, the theory you get has the symmetry of electromagnetism, U1.
Okay.
But if you have, say, a stack of multiple parallel D-branes, then you can have strings stretching between different branes in the stack. And these different types of connections generate the more complex symmetries, like SU2 for the weak force or SU3 for the strong force.
So the specific forces depend on how many branes there are and how they're arranged in the hidden dimensions. Another case of geometry dictating physics.
Exactly. And this D-brane picture also offers a potential solution to the hierarchy problem.
Which is, why is gravity so incredibly weak compared to the other forces?
Yes. The brain world scenario suggests maybe our universe, with all its matter particles and the electromagnetic weak and strong forces, is confined to a three-dimensional D-brane, a three-brane.
So we, and most of physics, are stuck on this membrane.
The idea is that the open string's responsible for us, and those forces are stuck. Their endpoints are on our brain.
But gravity,
Yeah.
they came from closed strings? Are they stuck?
No. Closed strings, like the graviton, are not tied to D-branes. They can travel freely through all the dimensions, our large ones and the extra compact ones, the whole higher dimensional space, sometimes called the bulk.
So gravity's influence spreads out into those extra dimensions.
That's the potential explanation. Gravity is effectively diluted because its force spreads across the full 10 or 11 dimensions. Meanwhile, the other forces are concentrated on our three-brane.
Making gravity appear much weaker to us living on the brain.
It's an elegant geometric picture, offering a reason for that vast difference in strength.
Wow. Okay, pulling it together. One type of string, vibrating in higher dimensions whose shape dictates the rules, gives rise to all particles. Closed strings give gravity, open strings stuck on D-branes give other forces, and maybe gravity seems weak because it leaks into the extra dimensions. That sounds incredibly neat. Almost too neat.
And that brings us squarely to the difficulties, because while the mathematical structure is compelling, your sources are very clear. String theory is fraught with significant challenges.
Number one being, we haven't actually seen any of this. No strings, no extra dimensions, no supersymmetry.
That's the unavoidable, most persistent and damaging criticism. A complete lack of direct or indirect experimental verification.
The energy needed to see a string directly is the Planck energy,
Right.
Which is just astronomical.
Way beyond anything we can reach. Your source mentions needing an accelerator the size of the galaxy, so direct observation is off the table for the foreseeable future, maybe forever.
What about indirect signs? Supersymmetry was a big hope, wasn't it? Finding those superpartner particles.
It was, and many string models do predict Siri Y should appear at energies the Large Hadron Collider could reach. But
Nothing.
despite extensive searches, as the sources state, no sign of Sui Y has been found. Now, that doesn't kill Zeus Y entirely. Maybe the superpartners are heavier than we thought, but it has ruled out the simplest and most natural versions and puts tight constraints on the remaining possibilities.
Which feeds into this really serious philosophical critique. Is string theory even falsifiable? If you can't test its core predictions directly, and the indirect ones aren't showing up.
It's a major debate. Can it be tested in the traditional scientific sense, as philosopher Karl Popper defined it? Critics argue its flexibility and the inaccessible energy scales mean it's effectively insulated from experimental refutation.
Making it hard to prove wrong. Which led some physicists to say it's not even wrong.
That's a famous, rather harsh critique, yes. It highlights the frustration. If a theory is so slippery you can't pin it down with experiments, is it really doing physics? Or is it more like mathematical philosophy?
It's a deep question about what counts as science when you can't do the usual experiments.
It really is. It's a profound philosophical schism in the field.
And then there's the huge problem within the theory itself, the landscape problem, related to those curled up dimensions.
Exactly. We said the shape of the Calabi-Yau manifold determines the physics. The problem is, mathematically, there isn't just one ship that works, or one way to arrange the D-branes.
How many possibilities are there?
The estimates are, well, they're staggeringly vast. Your sources cite numbers like 10 raised to the power of 500, maybe even more.
10.
Yeah.
With 500 zeros after it. I can't even comprehend that number. More than atoms in the universe, way more.
It's essentially an unimaginably huge number of different possible ways to compactify the extra dimensions, and each distinct way leads to a different vacuum state, effectively, a different possible universe with different particles, different forces, different constants of nature.
So instead of predicting our universe, string theory seems to predict this colossal landscape of possible universes.
That's the problem. If the theory allows for 10 in theory as different outcomes, how do we explain why our specific universe, with its specific laws and particles, is the one we see.
Without a mechanism within the theory to select our vacuum state.
The theory loses its predictive power. If it can explain almost anything, then it doesn't really explain our specific thing. This is widely seen as the single greatest theoretical hurdle the theory currently faces.
People talk about the anthropic principle here, right? Like, we see this universe because it's the only kind that allows life like us to exist to observe it.
That's one way people try to deal with the landscape, yes. But many physicists find it unsatisfying. It feels like giving up on prediction, a philosophical retreat. It doesn't explain why the laws are what they are from first principles.
And even M theory, the supposed unifier.
Yeah.
It's not fully understood either.
That's another layer of difficulty. M theory elegantly connects the 5 superstring theories, but we don't actually know its fundamental equations or principles. We understand its edges, its limits, where it looks like one of the string theories, but the core is unknown.
So we know the answers in certain regimes, but not the fundamental question M theory is supposed to answer. Feels backward, as one source put it.
There's no complete non-perturbative definition. We're still piecing it together.
Okay, so huge challenges, no direct evidence, falsifiability questions, this enormous landscape problem undermining predictive power. And the underlying theory isn't even fully known, given all that. Why are so many brilliant people still working on it? Why is it still such a focus?
Because, honestly, despite all those very real problems, it remains the most promising framework we have for unifying quantum mechanics and gravity. Its mathematical consistency, the way gravity emerges naturally, the potential for unification, it's still unparalleled.
So the potential payoff is just too big to ignore.
Exactly. And research is very active. People are trying to tackle these challenges head-on, exploring new theoretical avenues and looking for new ways to potentially test it. It's a vibrant and active area.
What kind of new directions are mentioned in the sources? Anything promising?
Well, there's the Bootstrap program, which is quite interesting. It takes a different approach.
Oh, bottom-up approach.
Yeah. Instead of starting with strings, it asks, forget strings for a moment. What are the most general mathematical rules any consistent quantum theory involving gravity must obey? You start with fundamental principles, Lorentz invariance, unitarity, causality.
And see what kind of theories are even possible.
Right. And remarkably, recent work has shown that if you impose these very basic consistency conditions, the mathematical formulas describing how particles scatter seem to be forced to take the form first discovered in string theory.
Whoa. So basic consistency might just lead you inevitably to string theory.
It hints at that possibility, a sort of logical inevitability. It suggests string theory might not just be one way to combine quantum mechanics and gravity, but perhaps the only consistent way. That's a powerful, though still developing, argument.
That's fascinating. A theoretical argument for why it has to be right.
Huh.
Are there computational approaches?
Yeah.
Like using AI for the landscape?
Yes, absolutely. Given the sheer vastness of the landscape, researchers are using AI and machine learning techniques to navigate it.
Trying to find
What?
our universe in that sea of possibilities.
Trying to see if solutions that look like our universe with the right particle content forces, maybe even the cosmological constant, are common or incredibly rare. Or perhaps find a specific Calabi-Yau shape and brain setup that matches everything we know. It's a huge computational task, but maybe AI can find patterns humans miss.
Okay, so theoretical arguments and computational searches. What about actual observations? If particle accelerators can't reach the Planck scale, where else could we look?
The best bet is cosmology, the very early universe.
The Big Bang.
Right after the Big Bang, during the period of cosmic inflation. Energies were near the Planck scale then, so the early universe acted as a natural, unique laboratory. String theory, if correct, might have influenced how the universe expanded and cooled, leaving faint, indelible signatures that we could potentially observe today.
What kind of signatures are we talking about?
Things like specific, subtle patterns, non-standard deviations in the temperature fluctuations of the cosmic microwave background radiation, the CMB. Future, more precise CMB telescopes might be able to spot them.
Okay, tiny heat variations from the dawn of time. Anything else?
Possibly a unique spectrum of primordial gravitational waves generated during that stringy era. Different theories predict different patterns of gravitational waves from the early universe. Detecting them and mapping their properties could give us clues.
And maybe even dark energy. That feels like a huge mystery string theory might touch.
It's more speculative, but yes. Some string theory models try to connect the physics of the extra dimensions and the Planck scale to the observed acceleration of the universe's expansion, which we attribute to dark energy. If those models make specific predictions about how dark energy behaves over time, future cosmological surveys could test them.
So it sounds like the path forward isn't going to be one eureka moment, one single experiment that says, yes,
Hmm.
strings.
Probably not. It's more likely to be, as your source suggests, a long and subtle process, building a cumulative case. From continued progress on the theory's mathematical consistency, maybe stronger arguments for its logical inevitability via things like the bootstrap, and hopefully detecting some of those faint whispers from the cosmos, hints in the CMB, gravitational waves, or dark energy measurements that align with string theory predictions and not simpler alternatives. It requires advances on all fronts: theory, math, and observation.
So wrapping this deep dive up, based on everything we've discussed from these sources, we're left with this incredibly compelling, almost poetic idea. The universe as a symphony, played by just one type of fundamental string.
Where all the particles, all the forces, even gravity itself just emerge as different vibrational notes. It offers this profound vision of unity, solving that core conflict between general relativity and quantum mechanics.
The mathematical elegance is undeniable. The potential explanatory power is huge.
It truly is. It's the only framework we know that seems capable of consistently describing quantum gravity.
But, and it's a massive but, we have to face those profound challenges, the stark lack of any direct experimental evidence, the real questions about whether it's even testable scientifically.
And that overwhelming landscape problem. The 10-year agrees possible universes, which makes it incredibly hard for the theory, as it stands, to predict the specific features of our universe from first principles. String theory is a leading contender, yes, but it is absolutely not proven.
The dissonance is huge. So the ultimate fate of this beautiful cosmic symphony idea, it really hangs in the balance, doesn't it?
It hinges on resolving these fundamental questions. Can we find clever new ways to test it, even indirectly? Can we understand the landscape or find a principle that selects our vacuum?
It leaves you wondering, does the universe really only have one possible tune dictated by mathematical consistency, as the bootstrap hints? Or is string theory describing this vast multiverse, this infinite chord, and we just happen to be living in one specific note that allows us to exist?
That's the multi-trillion-dollar question, isn't it? The final answer, the final notes of this symphony. They await future breakthroughs. In theory, in mathematics, and maybe, just maybe, in finding those echoes from the very beginning of time.